Good day, and welcome to this special deep dive report. The date is December 23rd, 2025. As the world awakens to another crisp winter day, the interstellar comet 3I Atlas, only the third confirmed visitor from beyond our solar system, is quietly slipping further into the cosmic void. It is leaving astronomers and speculators alike pondering its enigmatic journey. Tonight, we are going to strip away the headlines and look directly at the raw data to understand exactly where this object is, what it is doing, and why it matters so much to our understanding of the universe. Right now, at this very moment, on December 23rd, the comet is positioned in the constellation of Leo. If you were to pull up a star chart, you would find it at coordinates of right ascension, 10 hours, 29 minutes, 45 seconds, and declination, plus 8 degrees, 26 minutes, 16 seconds. For observers in much of the northern hemisphere, it is hovering below the horizon until the evening rise times. It is a silent traveler moving against the backdrop of the Lion, a constellation that has watched over humanity for millennia. But unlike the stars that make up that familiar shape, 3I Atlas is a transient ghost, here for a fleeting moment in cosmic time before vanishing forever. Just 4 days ago, on December 19th, 2025, 3I Atlas made its closest approach to Earth. It passed at a distance of approximately 269 million kilometers. To put that in perspective, that is roughly 1.8 times the distance between the Earth and the Sun. It was not a near miss in the Hollywood sense, but in astronomical terms, for an object that traveled light years to get here, it was an intimate encounter. As many people now turn their thoughts toward year-end reflections and holiday gifts from family and friends, some have half-jokingly wondered whether this cosmic interloper might deliver an interstellar gift of its own. Let's look closer at the data regarding this gift. The timing is poetic, certainly. A visitor from the stars arriving just before the holidays. But science deals in probabilities and physical laws, not poetry. The trajectory of 3I Atlas has been scrutinized by every major telescope on Earth and in space. We have tracked its path with a precision that would have been impossible just a decade ago. And what we see is an object that is indifferent to our calendar. It is following a hyperbolic path, a curve so open that it guarantees the comet will never return. It is a one-way ticket through the solar system. If you are enjoying this deep dive into the mechanics of our universe, please consider subscribing to the channel. We are dedicated to bringing you the science behind the headlines, unpacking the complex reality of space exploration without the hype. Your support helps us keep these investigations going. Now, back to the comet. The question on everyone's mind, fueled by social media speculation and the natural human desire for connection with the cosmos, is simple. Is it leaving anything behind? When a comet passes through the inner solar system, it warms up. The ices that have been frozen for eons begin to sublimate, turning directly from solid to gas. This process releases dust and rocks, creating the beautiful tails we associate with comets. 3I Atlas is no exception. It is shedding material. But where is that material going? Here is the crucial detail that often gets lost in the excitement. The dynamics of interstellar objects are governed by their immense speed and the specific geometry of their approach. 3I Atlas came in fast, and it is leaving fast. Its speed relative to the Sun is staggering. This high velocity means that any material it sheds retains that momentum. It is not like dropping a wrapper out of a car window where it falls to the side of the road. It is more like firing a bullet from a moving jet. The debris travels with the parent body. However, the interaction is not just gravitational. We have to consider the solar wind, the stream of charged particles flowing out from the sun, and the pressure of sunlight itself. These forces act on the dust and gas released by the comet. For a normal comet, like Halley or Neowise, we understand these interactions very well. We can predict meteor showers years in advance because the debris trails are laid down in predictable orbits that Earth intersects. But 3I Atlas is different. It is not in a closed orbit. Its trail does not form a closed loop that we can cross year after year. It is a single streak across the solar system. So, what does this actually mean for the interstellar gift hypothesis? It means that for Earth to receive any material from 3I Atlas, we would have to be in exactly the right place at the right time to intercept the wake of a ship that is moving faster than anything we have ever built. The geometry of the encounter on December 19th placed us 269 million kilometers away. That is a vast ocean of emptiness. For material to bridge that gap, it would need to be ejected from the comet with incredible force, or be subject to forces that push it directly toward us. This contradicts what we previously thought about how comet tails behave in these hyperbolic encounters. Early models suggested that perhaps the solar wind could fan the tail out broadly enough to dust the Earth. But as we refine our models with data from the James Webb Space Telescope and other observatories, the picture tightens. The stream of particles is more confined, more disciplined by the physics of the comet's high velocity. The gift, it seems, is staying wrapped up in the comet's own gravitational and kinematic influence. In more concrete terms, the question arises, could any material shed by 3I Atlas actually reach Earth? The concern is not entirely frivolous. We know that comets are chemical factories. They carry the building blocks of solar systems: water, carbon monoxide, methane, and more complex organic molecules. If 3I Atlas formed around a different star, its chemical composition is a direct sample of that alien environment. Receiving a sample of that material would be the scientific coup of the century. It would be like having a piece of an exoplanet delivered to our doorstep. But there is a darker side to this speculation. Spectroscopic observations have shown that the gaseous plume surrounding 3I Atlas contains cyanide and hydrogen cyanide. The latter is a highly toxic compound, historically used as a chemical weapon during World War I. The mere mention of cyanide triggers a primal fear. It shifts the narrative from interstellar gift to cosmic poison. At first glance, the idea of such material drifting toward Earth might sound unsettling. It evokes scenarios from science fiction where a passing celestial body brings a plague or a toxic cloud. We need to separate the chemical reality from the fear. Yes, cyanide is present. It is actually quite common in comets. We see it in comets from our own Oort cloud all the time. It is a simple molecule, carbon and nitrogen, easy to form in the cold depths of space. Its presence in 3I Atlas confirms that the chemistry of other star systems is not wholly unlike our own. But the presence of a toxin in a comet 269 million kilometers away is very different from that toxin being in our atmosphere. To understand the risk, or lack thereof, we have to look at the density of space. Space is, to a very good approximation, empty. A cloud of gas released by a comet expands rapidly. As it expands, it becomes incredibly diffuse. By the time any gas from 3I Atlas could theoretically traverse the distance to Earth, the individual molecules would be so far apart that they would be undetectable. It would not be a cloud, it would be a vacuum slightly less empty than usual. But we cannot just wave our hands and say, space is big. We need to run the numbers. We need to look at the mass loss rate, how much stuff the comet is actually throwing off, and the forces acting on that stuff. This is where the story gets interesting and where the physics provides a definitive answer that cuts through the fear. The interaction between the solar wind and the cometary ions is the key. As we prepare to delve into the specific physics of this poison cloud myth in the next chapter, keep in mind the scale of what we are discussing. We are tracking a mountain of ice and rock, tumbling through the dark, shedding a faint veil of gas, while our planet orbits safely millions of kilometers away. The universe is violent and toxic in many places, but it is also governed by laws that keep us isolated from most of those dangers. In the next segment, we will rigorously examine the poison cloud scenario. We will use the latest measurements from the James Webb Space Telescope to calculate exactly how far that cyanide gas travels before it is blown away by the sun. We will see why the solar wind is our greatest shield and why the physics of the solar system makes the transfer of gas from 3I Atlas to Earth not just unlikely, but physically impossible. Stay with us as we dismantle the myth and reveal the invisible forces that protect our world. Welcome back. In the previous chapter, we established the context of 3I Atlas's journey through Leo and the public fascination and slight trepidation surrounding its closest approach on December 19th. We touched on the detection of cyanide and hydrogen cyanide in the comet's coma, a discovery that has fueled some anxiety about an interstellar payload drifting toward Earth. Now, we are going to dismantle that fear, not with reassurance, but with hard physics. Let's look closer at the data regarding this chemical composition. Spectroscopic observations have indeed confirmed the presence of cyanogen, Cn, and hydrogen cyanide, HCN. These are simple organic molecules consisting of carbon and nitrogen. In the context of a laboratory on Earth, hydrogen cyanide is deadly. It interferes with the body's ability to use oxygen. It is a terrifying substance, but context is everything. In the context of a comet, it is a standard building block. We saw it in Comet Halley. We saw it in Comet Hale-Bopp. It is a signature of the primordial soup from which planetary systems form. The fear is that this poison cloud could detach from the comet and drift across the 269 million kilometers separating us, eventually settling into our atmosphere. To understand why this cannot happen, we have to look at the environment the comet is moving through. It is not moving through still air. It is moving through the heliosphere, the domain of the sun. The sun is constantly emitting a stream of charged particles, protons and electrons, known as the solar wind. This wind blows outward at speeds ranging from 300 to 800 kilometers per second. When gas molecules are released from the nucleus of 3I Atlas, they are initially neutral, but very quickly they are ionized. Ultraviolet light from the sun knocks electrons off these molecules, giving them an electric charge. Once they are charged, they are no longer free to drift. They become enslaved to the magnetic field lines carried by the solar wind. This is the crucial detail. The moment that gas becomes ionized, it is swept up by the solar wind and carried radially outward, away from the sun. Measurements of the comet's mass loss rate, including those obtained by the James Webb Space Telescope, allow us to calculate the stopping distance of these gas ions. This is the distance a gas molecule can travel from the comet nucleus before it is fully picked up by the solar wind. The data indicates that the gas emitted by 3I Atlas is swept up within just a few million kilometers of the comet itself. So, what does this actually mean? It means the comet is surrounded by a bubble of its own gas that is relatively small in astronomical terms. Beyond that bubble, the gas is stripped away and accelerated out of the solar system, moving away from the sun and away from Earth. The stopping distance is more than an order of magnitude smaller than the 55 million kilometers separating 3I Atlas's trajectory from the circle traced by Earth's orbit around the sun. Let's visualize this. Imagine the comet is a boat moving across a rushing river. The gas it releases is like dye dropped into the water. The dye might spread out a little bit around the boat, but the current of the river, the solar wind, instantly grabs it and carries it downstream. Earth is on the other side of the river, far upstream or parallel to the flow. There is no physical mechanism for the dye to swim across the current and reach the other bank. The flow of the solar wind is the dominant force, and it provides a hard barrier that the gas cannot cross. This contradicts what we previously thought might be possible if the solar wind were weaker or the comet's output were vastly higher. If 3I Atlas were erupting with the violence of a supervolcano, perhaps it could overwhelm the local solar wind. But the data from Webb shows a modest, steady outgassing. It is active, yes, but it is not a monster. The physics is robust. None of this gas ever comes close to our planet. Before we move on to the question of solid debris, I want to hear from you. We often hear about the dangers of space, asteroids, radiation, solar flares. Does the idea of interstellar contamination worry you? Or do you trust the vast distances of space to keep us safe? Drop a comment below with your thoughts. I read through them to see what aspects of these deep dives resonate with you. Now, having dealt with the gas, we must address the solid matter. Dust. Comets are often described as dirty snowballs, and as the ice sublimates, the dirt is released. Dust behaves similarly to gas, but with a twist. It is not affected by the magnetic field of the solar wind in the same way, but it is affected by light. Solar radiation pressure is a force we rarely encounter in daily life, but in space, it is powerful. Photons of light from the sun hit dust particles and push them. For very small particles, those smaller than a micrometer, like smoke, this pressure is overwhelming. It blows them out of the solar system faster than gravity can pull them in. These tiny grains are rapidly expelled. They form the straight blue ion tails and the diffuse dust tails we see in photos. Larger grains, millimeter scale or above, are less affected by sunlight or the solar wind. They have enough mass that their momentum carries them along the comet's path. This is where the geometry becomes our shield. Remember, 3I Atlas is on a hyperbolic trajectory. It is not in an orbit that crosses Earth's path. It is passing above the plane of the solar system, the ecliptic, and diving down or cutting through at a steep angle. Even if these larger grains were to intersect Earth's path, we have a second line of defense, our atmosphere. A millimeter-sized grain hitting the atmosphere at cometary speeds, tens of kilometers per second, contains a lot of kinetic energy. But it is small. It would burn up instantly. We see this every night as meteors or shooting stars. These are usually grains of sand from comets that passed by centuries ago. If 3I Atlas shed millimeter-sized dust that hit us, it would result in a nice meteor shower. Nothing more. It would be a light show, not a catastrophe. To pose a threat, the debris would need to be substantial. We are talking about meter-scale objects, boulders, essentially. These would be large enough to potentially survive atmospheric entry, or at least cause a significant airburst, like the Chelyabinsk event in 2013. But do comets release boulders? And if they do, what are the odds of one hitting us? This brings us to the realm of statistics. We can estimate the total mass lost by the comet and the size distribution of the particles. Most of the mass is in fine dust. The fraction of mass in large boulders is tiny. Given the measured mass loss rate of 3I Atlas, we can calculate the upper limit on how many large fragments could have been released. The numbers are reassuring. Fewer than 1 million such large fragments could have been released in recent months. That sounds like a lot, but they are spread across an enormous volume of space, a volume measured in cubic astronomical units, originating from distances exceeding twice the Earth-Sun separation. Even the closest of these hypothetical fragments would never approach Earth nearer than 10 Earth radii. 10 Earth radii is about 64,000 kilometers. That is a safe miss, and that is the closest hypothetical fragment in a worst-case scenario distribution. The probability of impact is effectively negligible. It is not zero, because in space nothing is ever zero, but it is as close to zero as you can get without using the word impossible. So, we have ruled out the poison gas. We have ruled out the dust. We have ruled out the boulders. Physics and statistics have built a fortress around Earth, protecting us from the physical debris of 3I Atlas. But all of these conclusions, of course, rest on one key assumption, that the released material behaves as passive debris. We are assuming it is just dumb rock and ice, obeying Newton's laws and the pressure of sunlight. But what if it isn't? What if the material or the comet itself is capable of maneuvering? That caveat brings us back to the more speculative edge of the discussion. It opens the door to a hypothesis that has been controversial since the arrival of the first interstellar visitor, Oumuamua. Could 3I Atlas be something else entirely? In the next chapter, we will leave the comfortable certainty of solar wind physics and enter the debate that has divided the astronomical community. We will look at the arguments for artificiality, the strange trajectory quirks, and why some scientists refuse to close the book on the idea that we are being watched. We have established that the gas and dust from 3I Atlas pose no threat to Earth. The solar wind acts as a broom, sweeping away the toxic cyanide, and the vast distances combined with orbital mechanics ensure that any solid debris misses us by a comfortable margin. We used the term effectively negligible to describe the risk. But let's dig deeper into that term. In science, negligible is a powerful word, but it requires rigorous backing. We need to understand the impact calculus, the specific math that allows us to sleep soundly while a mountain-sized object flies through our neighborhood. As we established, the primary defense against large debris is the sheer volume of space. It is difficult for the human mind to comprehend just how empty space is. We see diagrams of the solar system with planets and comets drawn as large spheres, making it look crowded. In reality, if the Earth were the size of a pea, the Sun would be a beach ball over 100 meters away, and 3I Atlas would be a grain of salt passing kilometers in the distance. The target, Earth, is tiny compared to the void. Let's look closer at the data regarding the mass loss rate, which is the variable that drives this entire calculus. The James Webb Space Telescope and other observatories measure the brightness of the comet and the density of its tail to estimate how much mass it is shedding per second. For 3I Atlas, this rate is consistent with a standard cometary body. It is not disintegrating. It is not shedding its skin in massive chunks. It is sublimating steadily. If we take the total mass lost over the months it has been in the inner solar system and model it as a cloud of debris, we have to distribute that mass across the size spectrum. The vast majority of particles are microscopic. The number of particles drops exponentially as the size increases. For every billion dust grains, there might be one pebble. For every billion pebbles, one boulder. When we run the simulation, assuming the debris is ejected isotropically in all directions, or even preferentially toward the Sun, which is typical for comets, the resulting cloud is tenuous. We calculated that fewer than 1 million fragments larger than a meter could have been released. Now, take those 1 million fragments and scatter them over a sphere with a radius of 200 million kilometers. The density of fragments becomes vanishingly small. Here is the crucial detail: the ejection velocity. When a piece of rock breaks off a comet, it doesn't just stay there. It is pushed away by the expanding gas. But this push is gentle. The ejection velocity is typically only a few meters per second relative to the comet. This means the debris stays very close to the comet's own trajectory. It doesn't fan out into a wide shotgun blast that covers the whole sky. It remains a tight beam. Since 3I Atlas's trajectory does not intersect Earth's orbit, it misses us by 55 million kilometers at the closest point of the orbit's projection. The debris stream also misses us by roughly that same distance. A few meters per second of drift over a few months only amounts to a few thousand kilometers of deviation. That is nowhere near enough to bridge the 55 million kilometer gap. So, what does this actually mean? It means that for a piece of 3I Atlas to hit Earth, it would need to have been ejected with a velocity of kilometers per second, directed precisely at us months ago. There is no natural mechanism for a comet to shoot a rock at Earth like a cannonball. Natural outgassing is a gentle push, not an explosion. This contradicts what we previously thought might be a risk factor, the idea of fragmentation events. Sometimes comets do break apart. Comet Atlas C219Y4, a different object entirely, disintegrated famously. If 3I Atlas were to shatter completely, the debris cloud would expand. But even then, the center of mass of that cloud would follow the original orbit. The expansion would have to be incredibly violent to reach Earth. And we have seen no signs of fragmentation. The nucleus remains intact. The heart of the comet is beating steadily. However, we must be thorough. We mentioned meter-scale sizes. Why is that the cutoff? Objects smaller than a meter burn up. Objects larger than a meter can survive to the ground or explode in the lower atmosphere. The Tunguska event in 1908 was likely caused by an object 50 to 60 meters across. The Chelyabinsk meteor was about 20 meters. 3I Atlas itself is likely only a few hundred meters to a kilometer across. It simply doesn't have the mass to spawn a fleet of Tunguska-class impactors. It would have to shed a significant percentage of its total mass in huge chunks to produce even a single threat, and we would see that happening. The comet would dim or change shape dramatically. It hasn't. The statistics are overwhelmingly in our favor. The probability of an impact from a fragment of 3I Atlas is lower than the probability of being hit by a random asteroid that we haven't discovered yet. It is a risk that disappears into the background noise of cosmic hazards. But there is a lingering question in the back of the mind. We are modeling this object as a dirty snowball, a mix of ice and rock that obeys the laws of thermodynamics and gravity. We assume the mass loss is driven by the sun warming the ice. We assume the trajectory is determined solely by the sun's gravity and the slight rocket effect of the outgassing. All of these conclusions, of course, rest on one key assumption: that the released material behaves as passive debris, incapable of maneuvering via technological propulsion. That caveat brings us back to the more speculative edge of the discussion. What if the outgassing isn't outgassing? What if the trajectory isn't just gravity? At present, 3I Atlas is about 269.9 million kilometers, 1.804 AU from Earth, and that distance is steadily increasing. It is racing outbound. But as we track it, we look for anomalies. We look for things that don't fit the dirty snowball model. And there are scientists who argue that we shouldn't be so quick to dismiss the anomalies we do see. Fresh observations from the Comet Observers Database, SOBS, updated as recently as December 21st, reveal that the object remains active. It sports a coma 2.2 arc minutes across and a tail extending 7.8 arc minutes. These are clear signs of activity. But is it natural activity? In the next chapter, we are going to explore the artificial hypothesis. We will look at the work of Harvard astrophysicist Avi Loeb and others who suggest that objects like 3I Atlas might not be rocks at all. We will examine the non-gravitational acceleration, the tiny push that comets feel, and ask if it could be the signature of an engine. We will look at the extreme geometry of its arrival and ask, was this a random flyby or a targeted scan? The line between science fiction and cutting-edge science is often defined by data, and the data on interstellar objects is strange enough to keep that line blurry. Join us as we step into the unknown. We have crunched the numbers on impact probabilities and found them comforting. We have analyzed the chemical composition and found it toxic but distant. By all conventional metrics, 3I Atlas is a natural object, a shard of ice and dust ejected from a dying solar system eons ago, passing through ours by sheer chance. But science thrives on challenging conventions, and when it comes to interstellar visitors, the convention is still being written. We have only seen 3 such objects in history. A sample size of 3 is hardly enough to establish a normal. This brings us to the alien artifact debate. It is a conversation that moved from the fringes to the mainstream with the arrival of Oumuamua in 2017, and it has reignited with 3I Atlas. The core of the debate hinges on the passive debris assumption. We assume the object is dead, tumbling, and reacting blindly to the sun. But what if it isn't? Harvard astrophysicist Avi Loeb, well known for his provocative ideas regarding extraterrestrial technology, has suggested that we need to keep an open mind. He argues that if we only look for rocks, we will only find rocks. We must consider the possibility that 3I Atlas's extreme hyperbolic trajectory, boasting an eccentricity of 6.14, could be a sign of something more. Let's look closer at the data regarding this eccentricity. In orbital mechanics, an eccentricity of 0 is a perfect circle. Between 0 and 1 is an ellipse, like Earth or Halley's Comet. Exactly 1 is a parabola. Anything greater than 1 is a hyperbola, an open path that never returns. Oumuamua had an eccentricity of about 1.2. Comet Borisov, the second visitor, had about 3.3. 3I Atlas has an eccentricity of 6.13. This is extreme. It means the object is moving incredibly fast relative to the Sun. It is punching through the solar system with immense energy. Loeb suggests that this high speed and the object's apparent indifference to Earth during closest approach could, in principle, be consistent with an artificial probe. In Loeb's words, this could represent a kind of blunt message in a bottle, passing through our system without slowing down or deviating. The idea is that a defunct probe, or perhaps a buoy in a vast interstellar network, wouldn't necessarily stop to say hello. It would just drift, carrying its data or its message, powered by the kinetic energy of its launch millions of years ago. This contradicts what we previously thought about first contact. We always imagined ships landing on the White House lawn or radio signals pulsing prime numbers. We didn't imagine silent, dark shapes rushing past the sun and ignoring us. But if the galaxy is billions of years old, it could be littered with such debris, technological trash, rather than active explorers. Here is the crucial detail that fuels the speculation: the non-gravitational acceleration. Comets are pushed by the rocket effect of outgassing. We see this with 3I Atlas. It is deviating slightly from a pure gravity-only path. Mainstream astronomers attribute this to the sublimation of ice we discussed earlier. The gas shoots out one way, the comet moves the other. It fits the model. But proponents of the artificial hypothesis ask, is the outgassing sufficient to explain the push? Or is there an excess acceleration? With Oumuamua, there was no visible tail, yet it accelerated. That was the smoking gun for Loeb. A push without a propellant implies a solar sail or some other mechanism. With 3I Atlas, we do see a tail. We see the propellant. This makes the natural explanation much stronger. The visible coma and tail, detected by COBs and major observatories, provide a mechanism for the movement. Yet, speculation persists. Some have pointed to subtle irregularities in tail activity detected by ESA's XMM Newton on December 3rd as potential anomalies. The X-ray emissions from comets are usually caused by the solar wind slamming into the comet's atmosphere. Variations in this emission can tell us about the density and composition of that atmosphere. The irregularities could be interpreted as sputtering or pulsed activity. So, what does this actually mean? Mainstream astronomers remain unconvinced. They attribute these effects to natural cryovolcanism, jets of gas erupting from beneath the crust as the comet rotates, or asymmetric outgassing, where one side of the comet is more active than the other. Interactions with the solar wind can also be turbulent and chaotic, creating complex patterns that look like anomalies but are just fluid dynamics in space. Searches for technosignatures by projects such as Breakthrough Listen have so far yielded no evidence of artificial signals. We have pointed radio telescopes at 3I Atlas, listening for the telltale narrow-band transmissions that would indicate a transmitter. We have listened for radar pings. We have heard only the static of the universe, silence. But, as Loeb often points out, absence of evidence is not evidence of absence. A defunct probe wouldn't be transmitting. A passive sensor wouldn't be beeping. The silence doesn't prove it's a rock. It just proves it's not a radio station. The debate is healthy. It forces us to refine our models. It forces us to look closer. If we dismiss every anomaly as just a weird rock, we risk missing the most important discovery in human history. But if we cry alien at every shadow, we lose scientific credibility. The balance is found in the data, and right now, the data leans heavily toward natural. 3I Atlas looks like a comet, acts like a comet, and smells, chemically, like a comet. But it is a comet from somewhere else. And that alone is profound. It carries the history of a different star. It is a messenger, even if it is a dumb, frozen one. As we move to our final chapter, we must accept the reality of the situation. The window of opportunity is closing. 3I Atlas is leaving. It is fading. The chance to study it up close has passed. We are left with the data we have gathered and the questions that remain. In the next segment, we will look at the silent goodbye. We will track the comet's final trajectory as it heads back into the dark. We will discuss what we have learned, what we missed, and what this encounter teaches us about our place in the galaxy. The visitor is leaving the building, but the echoes of its passage will be analyzed for years to come. The debate over artificial origins may never be fully settled to everyone's satisfaction, but the physical reality of 3I Atlas is not up for debate. It is a physical object obeying the laws of motion, and it is leaving. We are now witnessing the silent goodbye of our interstellar guest. The excitement of the closest approach is behind us. The headlines are beginning to fade, but for the astronomers, the work is far from over. For now, 3I Atlas continues its silent passage through Leo, fading steadily as it retreats into interstellar space. It is a ghost drifting through the lion's mane. Projections indicate it will grow dimmer over the coming weeks. By early 2026, its distance from Earth will peak, and it will become a faint smudge visible only to the most powerful eyes on and off the planet. Eventually, it will disappear beyond the fringes of the Oort cloud, that vast shell of icy debris that surrounds our solar system never to return. Let's look closer at the data from the final leg of this journey. Major observatories are still paying close attention. The Hubble Space Telescope last imaged 3I Atlas on November 30th, capturing high-resolution views of the nucleus and coma. A broader NASA multi-mission campaign, including data from Europa Clipper, which is on its own journey to Jupiter, and MAVEN, orbiting Mars, has confirmed ongoing outgassing of hydrogen and dust. This multi-point perspective is crucial. By observing the comet from different angles, from Earth, from Mars orbit, and from the deep space trajectory of Clipper, we can build a 3D model of the outflow. We can see the shape of the tail not just as a flat projection on the sky, but as a volumetric structure. This reinforces the picture of a dynamically evolving object rather than a dormant relic. It is alive, in the geological sense, responding to the waning heat of the Sun. Fresh observations from the Comet Observers Database, COBS, show the magnitude dropping. It is currently at 1529. That is far beyond naked eye visibility. You need a large telescope to see it. As it moves away, the inverse square law of light takes its toll. It gets less sunlight to reflect, and it is further away from us seeing the reflection. It will fade into the blackness rapidly. So, what does this actually mean for the legacy of 3I Atlas? It means we have a limited data set. We didn't have a mission ready to intercept it. We couldn't launch a probe to land on it, or fly alongside it and scoop up a sample. We had to watch from a distance. This highlights a gap in our planetary defense and exploration capabilities. We are getting better at spotting these things, but we are not yet fast enough to catch them. However, the data we did get is a treasure trove. The spectra of cyanide and hydrogen cyanide, the dust production rates, the light curves. These are puzzle pieces. They tell us about the chemistry of the star system where 3I Atlas was born. Was it a star like our Sun? A red dwarf? A binary system? The isotopic ratios in the gas might hold the answer. We will be analyzing this data for decades. Whether it is merely an interstellar drifter, a frozen relic from a distant star system, or something more exotic, 3I Atlas serves as a powerful reminder of how much we have yet to learn. It reminds us that our solar system is not a closed box. We are porous. We are part of a galactic ecosystem where material is exchanged between stars. With no new outbursts reported today, the comet remains a tantalizing puzzle. It didn't break up. It didn't signal us. It just passed through. It urges humanity to keep watching the skies and asking difficult questions. It challenges us to be ready for the next one, because there will be a next one. The statistics say that interstellar objects are passing through the solar system all the time. We just usually miss them. Now that we know how to look, we will find more. The stars, after all, may yet whisper more. 3. I Atlas was a whisper we barely heard. The next one might be a shout. If you found this deep dive valuable, if you appreciate the effort to separate fact from fiction and fear from physics, please leave a like on this video. It helps the algorithm share this scientific perspective with more people. And if you haven't already, subscribe and hit the notification bell so you don't miss our next investigation. We are watching the skies, we are crunching the numbers, and we will be here to tell you what it all means. Until next time, keep looking up.